Okay, so the next speaker is Sergio Cecotti, and the title of his talk is N=2 gauge theories and algebras.
Thank you. So everything I will say is joint work with these people, in particular this second paper written with Kumrum Rafa, on which you can find details that I will skip. So let me first introduce an important class of four-dimensional n=2 models, which are the complete quiver theories. Quiver n=2 theories is a well-known subject. It's due to many people here. I just put some names to remember people that had worked on that line. And so there is a large class, not all of them, but a large class of four-dimensional n=2 theories, whose BPS states correspond to supersymmetric states of a one-dimensional quiver supersymmetric quantum mechanics. That is, they satisfy the conditions that the t terms and f terms are equal 0. From a four-dimensional point of view, this quiver Q is just a way of encoding the Dirac pairing between the charges, which are of various kinds, electric, magnetic, and flavor. So if I have a lattice of quantized charges, electric, magnetic, and flavor, just a lattice, so a free abelian group of rank R, and on this lattice I have a bilinear skew-symmetric pairing, which is given by the Dirac pairing, which is an integer by Dirac quantization, and this is a bilinear on this lattice. And to this data, I associate a quiver by taking one node for each generator of the charge lattice, so for each charge, and writing between the node I and node J a number of arrows which is equal to the respective Dirac pairing, with the convention that if this number is negative, the arrows goes in the other direction. Then the one-dimensional gauge group is just interpreted as the BPS charge vector, where the ranks became just the component of the charge vector in the charge lattice. And the central charge, in the four-dimensional sense, is a linear map from gamma to C, and of course the mass of the BPS state, by definition, is just the absolute value of the central charge evaluated on the vector, on the charge vector of that given particle. So this is just to fix the notation, and BPF states correspond to supersymmetric vacua, or equivalently to a stable with respect to the stability condition given by the central charge representation of this quiver, and in particular they satisfy the condition that the endomorphism equals C, and they are in particular irreducible in decomposable representation. However, the quiver Q is not unique because I am still free of doing one-dimensional cyber dualities, and so this leads me to introduce the notion of quiver mutation. And the quiver mutation is a product of a sequence of basic quiver mutations, and there is one such basic mutation for each node, which is essentially the cyber duality at that gauge group, and a mutation goes through four operations, inverse all the arrows through that node, and introduce new arrows when I have such a situation. I also delete the pairs of opposite arrows like this between the same pair of nodes, which means essentially that I give mass, and so will decouple states which are vector-like pairs of Higgs fields in one dimension. And finally, I have to replace the superpotential according to the rule of the cyber duality. Two quivers are said to be mutation equivalent if they are related by a chain of cyber dualities. And so a quiver n equal 2 theory is associated not to a single quiver, but to a full mutation class of quivers, where the mutation class are all the quivers that can be obtained one from the other by a chain of mutation. So these are just examples. The first two is, the first is, yeah, that is pure SU2, superior Mills, also called the Kronecker quiver, and this is n equal to 2 star. And these two have the properties that the class contains just one quiver. So these are unique quivers in the class. This is SU2 with one flavor, and here I have already two distinct quivers in the class, just two. But if I go to SUN, superior Mills, and I consider n larger than 2, I get an infinite class. So you see that going from this situation to this, I have a dramatic change in the nature of the problem. Okay, the central charge physically is a function of all physical parameters I have in the theory, so gauge coupling, masses, column branch coordinates, and so on. And changing the parameters, which also means changing the central charge, induce crossing, in general, walls of marginal instability at some position. And then we know that the BPS spectrum jumps according to the Kontsevich-Soibelman wall crossing formula. And also by going around in coupling constant space, sometimes I need to change the quiver to another one in the same mutation class. So this is the general structure of the problem. However, there is this fact that should be emphasized, that is that not all the consequences I get for the wall crossing formula are physical. This is true in 4 dimensions, it is true in 2 dimensions. And the reason is that although you have many BPS chambers at the mathematical level, because you take any linear function on the charge lattice, you define a stability condition from the point of view of mathematics, and you define a chamber. It is not true that all chambers that exist mathematically can also be realized as physical systems. This is due to the fact that the image of the map from the space of physical parameters that the theory has to the space of possible central charge, which is just C to the R, where R is the rank of the charge lattice, this need not to be surjective. So some stability conditions, some choices of central charge just cannot be realized for any choice of the physical parameters. And in general, the image of this as a positive codimension is a proper submanifold of this. This is formally decomposing a composition, a series, of BPS chambers, and mathematically the wall crossing formula works for all of them, but only a subset corresponds to physical situations that I can realize in general. Just because you have chambers in general which have zero intersection with the image of this map, and so no points in that BPS chamber correspond to physical situations. So, in general, to understand the physics of a model, it is not enough to solve the mathematical problem of stability or using the Kontsevich-Soibelman wall crossing formula. I have also to understand which of the formal chambers are physical and which are not. So, and this is an hard problem, very difficult in general. So there is a simple case, which are the complete theories. The complete theories are precisely the theories for which the map from the parameter space and the space of central charges is at least generically surjective. That is, essentially, all possible formal mathematical chambers, BPS chambers, can be realized as physical situation by choosing the parameters of the theory in some convenient way. So this is just heuristic, this discussion, but it gives a rough idea of what completeness is about. If you consider a theory which has a weakly coupled Lagrangian description, but this is just heuristic because almost all complete theories have no Lagrangian description, so that's just to give a rough idea. But if we have such a situation in which we have a Lagrangian description, we just come dimension. The rank of the charge lattice is given by the number of electric plus magnetic plus flavor charge, and so it is twice the rank of the gauge group plus the rank of the flavor group. And the dimension of the parameter space is the number of gauge coupling plus the dimension of the Coulomb branch plus the number of masses. And this gives me the number of simple factors of the gauge group, this, then the rank of G and the rank of the flavor group. So equating the two, I get the condition that the rank of the gauge group should be equal to the number of simple factors in the gauge group, and so the gauge group is SU2 to the M. This is heuristic, but it's true that for all complete theories, if you find a limit in which they behave like a weakly coupled Lagrangian theory, the gauge group will be of this form. Why are complete theories interesting? There are various reasons why they are interesting. The first one is that they can be completely classified. So we know well of which theory we are talking about, and also the classification itself is interesting. Second reason, many interesting models, which are interesting for other reasons, turn out to be complete, and so can be understood from this point of view. And the third reason is that to compute the non-perturbative physics, and not just the BPS spectrum, but many other quantities, for this theory in detail, really in detail, is both easy and elegant for this class of theory, just because I have not that problem of determining where is the physical region in central charge space. And last but not least, it is an ideal non-perturbative laboratory in the sense that we gain many non-perturbative insights on the n=2 theories, and also methods and results that can be extended to more general theories, that is, general groups larger, with rank larger than 2, and so on and so forth. So at the end, we want to understand n=2 theories in general, not just complete theories, but passing through the understanding of the complete ones as a special case is very convenient in order as a step to understand the more general ones. In particular, complete theory means ultraviolet complete. So classification, this is the first result. And the idea of the classification is very easy, and essentially works like this. If the theory is complete, by definition, we have enough physical deformations to give a large mass to all BPS states, but those having a charge vector of this form, where I take 2 generators of the lattice, and I take only states which have vectors, charge vector of this form, that is a linear combination of those 2 generators. And all the others, I get a large mass by choosing the parameters in some way. I can do because it is complete. So what I get, taking M to infinity, everything decouples, and I remain with an effective quiver, which contains just that 2 nodes that I had not put the mass to infinity, and as many arrows they had in the original quiver between them. But there is a result that was obtained in the first paper I quoted before, that quivers with 2 nodes correspond to consistent quantum field theory only if I have at most 2 arrows. So if there are more than 2 arrows between any 2 nodes, this is not consistent with completeness. And moreover, if it is complete, all quiver in the class, in the mutation class, correspond to physical regimes. So I get this necessary condition for the quiver of a complete n=2 theory. That is, the quiver of a complete theory has the property that all the quivers in its class have at most 2 arrows between any pair of nodes. This is a priori just a necessary condition. You can think that you need other conditions to add, or maybe that there are quivers of this form that do not correspond to any physical theory, but it will turn out that this is the only condition and that all quivers having this property will correspond to a physical theory that you can construct in one way or in the other, in particular by string engineering. And we are lucky because quivers with this property are classified. It is an important theorem due to these mathematicians, and they are just 2 classes. One is an infinite class, and is the class of all incidence quiver, that I will define in a moment, of ideal triangularization of borderer surfaces with punctures and marked point on the boundary. And then there are 11 exceptional mutation classes. This corresponds to the quiver, which are orientations of the Dinkin diagrams of E8, E6, E7, and E8. These correspond to the quivers which are orientations of the affine Dinkin diagrams E6, E7, E8. These are the same story, except that instead of being affine Dinkin diagrams, they are elliptic ones. That is, the corresponding Lie algebras are toroidal Lie algebras. In this case, we're affine, and this finite dimensional. And then there are 2 other guys. The number 6 and 7 is just the number of nodes. So this is the complete list. And all these quiver classes correspond to n=2 theories, which may be obtained by string methods, or some of them have just a Lagrangian description, and so can be constructed in this way. So the fact that this was a necessary condition and that we find an n=2 theory corresponding to each of them says that this is just the full list of complete quiver n=2 theories in 4 dimensions. Just to give the pictures, these are the 3 elliptic quivers in the standard form. Of course, there is a mutation class, which is big, but this is the typical way they are written. And this is X6 and X7, the last 2. And then all others are incidence quiver of an ideal triangularization of a surface. So the number of nodes of the quiver is just, or if you wish, there is a 1/1 correspondence between nodes of the quiver and arcs of the ideal triangularization. The number of arrows between node I and J is given by a sum over the triangle of which the 2 arcs are both sides, with a sign which is ±1 according to the relative orientation. And since at most the 2 arcs at most share 2 triangles, we know that this is bound in absolute value by 2, just because of this topological fact that we have at most 2 triangles contributing to this sum. Moreover, we have a theorem that says that ideal triangularization of a surface, 2 different ideal triangularization of the same surface have mutation equivalent quivers. So this property holds for the full mutation class. And so this means that all quivers that I can construct as in this way out of ideal triangularization of surface are complete in the sense I said before. The number of arcs is equal to the rank of the lattice and is given by this formula where G is the genus, P is the number of punctures, B is the number of components, of boundary components, and C is the number of marks on the boundaries. And we have a rule that says that each boundary component has at least one mark point, and the number of puncture plus the number of boundaries should be positive. We cannot have a surface which has no puncture and not boundary because we have no points to base the ideal triangulation. Okay, so this was the classification of the quivers, and now we can identify the n equal to 2 models. The first class, the ones which is given by the ideal triangulation of a surface with those numbers, turns out to be just the n equal to 2 model constructed using the technique of Gaiotto, Moore, and Aisky. That is, you take the A1 to 0 theory in 6 dimensions, you compactify on a curve of genus G, and you require that each quadratic differential has an ordinary double pole at each puncture, and a pole of order k plus 2 for a boundary component with k marked point. And these are superconformal precisely if you have no boundary, or if you have genus 0, one boundary, and p equals 0 and 1. And these are just Argyro-Douglas theories, and these are the conformal Gaiotto theories. The last two cases, I will not enter in details of the last two cases, but X7 is just a max deformation of the G equal to P equal B equal 0 model. So it is not strictly a model of this class, but is strictly related. It's just a mass deformation. And X6 is a decoupling limit of X7, so also it is of this class. The first is superconformal in the ultraviolet, and the second one is just asymptotically free. So with this kind of construction like Gaiotto-Moore-Naisky, we have almost all of these theories, including these two, if you allow these deformations, except for the 9, which correspond to the E's linking diagram. And so we are reduced to understanding only this, which are easy to understand because since they quiver are linking diagrams, we can use Lie algebraic methods in order to study them. So this is also explained the title of the talk, that we can reduce the analysis, taking into account that all these cases are already understood by these methods. All the remaining one, which are the E linking quivers in the 3 forms, finite dimensional, affine, and toroidal, can be understood using just Lie algebra. So my next subject is just understanding the n equal to 2 theories in 4 dimensions which are associated to Lie algebras, and in particular these 9 E-type exceptional complete theories which are associated to linking diagrams. But it is convenient not to consider these E's by themselves, but the full family of the n equal to 2 theories, which has a quiver, which is a mutation equivalent to a linking diagram with some orientation. So these are the complete theories which have a linking quiver. There are the finite dimensional ones, I mean in the sense of Lie algebra, which correspond to the ADE Argyro-Douglas model, which have no vectors, multiples in any chamber, have only hypermultiples, and are ultraviolet and superconformal. Then there are the affine dinking diagrams, and here it is irrelevant the orientation. All orientation gives cyber dual theories, so the same theory. For affine dinking quivers, the same is true for D and E, because the dinking diagrams are trees, but for the A's you have a cycle, so you have to say something about the orientation, and they are equivalent if you fix P and Q, where P is the number of arrows in the positive direction, and Q is the number of arrows in the negative direction, and you have to have at least one arrow in the negative direction. Otherwise, if you have a complete cycle, it is just equivalent to a Argyre-Douglas of D type. And then we have the elliptic dinking quiver, which correspond to toroidal Lie algebras. And here we have just 4 in this class. The first is D4, elliptic D4, which is just SU2 with 4 flavors. And then we have the 3E, elliptic E with R6, 7, 8. All these are ultraviolet superconformal SU2 gauge theories. For all these theories that can be studied in parallel, you have that the BPS spectrum has a Lie algebraic interpretation, because the charge lattice is just identified with the root lattice of the corresponding Lie algebra, just because the quiver is the dinking graph. So you have that the nodes are in one-to-one correspondent with the simple roots. And then if alpha in the charge lattice, that is the charge vector of a stable BPS, if alpha is the charge vector of a stable BPS particle, then alpha should be a root, in fact, a break root of the Lie algebra, respectively finite dimensional, affine, or toroidal, depending on which of the 3 situations you are. But the result is the same, except that, of course, the space of roots will depend in a very important way on the case. If the root is real, the BPS state is an hypermultiplet. If the root is imaginary, the state is a vector multiplet. Of course, if you have a finite dimensional Lie algebra, all roots are real, and so here you have not vector multiplets, you have only a hypermultiplet. In this case, you get, of course, vector multiplets just because they are essentially SU2 gauge theories, and so in weak coupling you find the W boson, which correspond to imaginary root. The first 2 class, finite dimensional and affine, are in particular Kac-Moody algebras. The third class is not are Lie algebra which are not Kac-Moody algebra, and for this, just because they are Kac-Moody, you find that there exists a strong coupling chamber with only BPS hypermultiplets, no vector multiplets, and having charge vector equal to the simple roots. This is known, for instance, for pure SU2, which correspond to P and Q equal 1, or for SU2 with 1 or 2 or 3 flavors, and this is just a particular case of this statement, which is true for all n equal 2 theories which are associated to Lie algebra, which are of the Kac-Moody type. And by this I mean that the Cartan matrices have off-diagonal entries which are non-positive. Instead, the third case have a Cartan matrices in which the sign of the off-diagonal elements are both positive and negative. And that is why it is not a Kac-Moody algebra. Okay. Except for the first class, the Argyre-Douglas model corresponding to a finite dimensional Lie algebra, all these have weakly coupled chambers with the W bosons, which is a vector multiplet. And in the G equals 0 limit, since it is complete, we have all parameters, then we can choose any limit we wish. We get a theory which is SU2 superior means, which are coupled to a set of matter, so to say, by gauging the global SU2 symmetry of a collection of D-type Argyre-Douglas system. The Argyre-Douglas of D-type have a global SU2 symmetry. You can quickly gauge that. And all theories of the kind described by Lie algebra are all of this form, except for the Argyre-Douglas, that they are one SU2, a bunch of Argyre-Douglas of D terms, and SU2 gauges the diagonal subgroup of all these SU2. And so this is the list. So the first class in particular contains SU2 with 0, 1, and 2 flavors for P and Q equal 1, 1, 2, 1, and 2, 2. The second class, the affine D, contains SU2 with 3 flavors when R is 4. Then you have this affines E's, which are SU2 coupled to 3 systems with this, where D2 means the empty matter just by convention. Well, D1 is the empty matter by convention. D2 is a fundamental hypermultiplet in this notation. So D4, 1, 1 is just SU2 with 4 flavors. And then we have these other 3 models, which are all conformal and correspond to SU2 coupled to D3 matter system, to D2, which is a standard hypermultiplet, 2 D4s, and here a hypermultiplet, and D3 and D6. And you check that this, which is the formula for the beta function contribution from the D type of matter, just give you positive here for these 3, which are the asymptotically free theory, and give 0 for these 4 here, which are the superconformal ones. So this is the explanation of the physics of the models which correspond to algebra, Lie algebra, and the way you get it is just computing the spectrum that you can do just using the Lie algebraic structure and taking the limit G equals 0 in the spectrum and see what you get in the decoupled limit, you get this. Of course, since the Ds have many chambers themselves, you get many different decoupled chambers. There is, however, a simple technique without going in solving the model and finding the spectrum, and of course give the same result, and this is the one we use in this paper. So we see that a Kronecker quiver, which means 2 nodes with 2 lines, has a stable BPS vector multiplet of charge, just the sum of the 2, if you are in this chamber, which is just a weakly coupled chamber, and you can add an extra, say, state, which is as a SU2 symmetry, engage it through this, and just by computing the Dirac pairing, you get this picture here. So whenever you have this picture here, this subquiver, where this ellipsis means whatever else is in the quiver, it means that you have something, the system you have here, and which is gauged by SU2. And for a complete theory, the only system you can gauge are Argyre-Douglas with SU of D type. And indeed, you can write the Dynkin quiver, mutating them in this form for A, D, and E type, and you say that this is one system gauged, this is another system, so this you have 2 systems, here you have 3, because you have these 2 elementary fundamental hypermultiplets, and then you have this system for D, and for the E's you have this kind of systems, which are just the table I presented before. So all these theories, which can be solved by Lie algebraic techniques correspond to SU2 superior mills coupled to 0, 1, 2, or 3 Argyre-Douglas systems. And the same is true for elliptic Dean quivers, except that for NF equal 4, you have 4 systems, of course. And just I show again the picture of the His, and you see that these are the systems connected with that triangle, which means that just gauging an SU2 global symmetry. Okay, but we can understand more these theories because, in particular, these elliptic Dean quivers have appeared in many places in the mathematical literature as root systems, as toroidal Lie algebras, but also as the Coxeter-Dinkin graphs of singularities. And indeed, it is known that they are the Coxeter-Dinkin graphs of the parabolic singularities, of the 3 parabolic singularities of Arnold, which are theirs. And so, another way of understanding these theories, or better to construct them, apart from gauging weakly the SU2 symmetries of the type Argyre-Douglas system, is to consider type 2B superstring on the local Calabi-Yau given by this W, X, Y, Z is this polynomial, plus U square equals 0. And this gives you, in this case, for instance, explicitly the Seiberg-Witten-Kirchhoff differential just by going instead in the construction starting from 6 dimensions. And from this, you can compute the quantum monodromy, the fractional monodromy. You can compute the strong coupling spectrum, and so on and so on, very easily. It was done in this paper. And in particular, you see not only that this theory is conformal, which was already understood, but also that they have strong coupling chambers in which you have a finite spectrum consisting only of a finite number of hypermultiplets, and you also know the charges of all of them, the quantum numbers, and so on and so forth. So these theories exist. They can be constructed in this way. They can be also understood and computed in another way, but you can also compute them using Lie algebraic theory, and the two are not completely independent because are related by these theorems here, which says that the same Dinkin diagrams enter in the two cases, and I mean, there are deep reasons why the same Dinkin diagrams appear in one theory, in the singularity theory, and in the Lie algebraic theory. Okay, so this is, I think, time for the conclusion. So the first conclusion is that the algebraic combinatorial methods are very powerful.